Hello, this is Richard Collins, your instructor in ATM 101 Weather and Climate of Alaska here at the University of Alaska, Fairbanks. Welcome to Unit 9, Weather Systems. Weather systems are the air masses, fronts, cyclones, and anticyclones that determine our weather. Like any system, weather systems are a group of weather elements that interact to form a complex whole. These systems form our framework for understanding and forecasting weather. The textbook identifies these as mid-latitude weather systems, as they are systems that are influenced by the Coriolis Force. The Coriolis Force increases with latitude and is weakest at the equator and strongest at the poles, and thus the weather systems influenced by the Coriolis Force are those in the mid and high latitudes. So these systems are not just confined to the mid-latitudes, but also define the weather in Alaska and the Arctic. In the first slide, we see a polar cyclone or low-pressure system revealed by clouds in an infrared satellite image. Polar lows are small, intense storms that form over open ocean during the cold season. Polar lows can look much like a hurricane, with a large spiral of clouds centered around an eye. For this reason, they are sometimes called Arctic hurricanes. Like hurricanes, these intense storms have heavy, showery precipitation that, unlike hurricanes, is in the form of snow. Polar lows range in size from about 100 to 500 kilometers, or 62 to 310 miles, in diameter. Wind speeds average around 50 miles per hour, although they can occasionally reach hurricane strength of 64 miles per hour. These storms form when cold Arctic air flows over warmer open water and meets warmer air. The boundary between the colder and warmer air, or in this case, very cold and cold air, is called an Arctic front. At the front, the warmer air rises and the colder air sinks. As the warm air rises, some of the water vapor condenses, releasing latent heat, and it further warms the atmosphere and lowers the surface air pressure. At the surface, there is a transfer of heat from the warm water to the cold air. This transfer of heat drives convective updrafts. The surface heating also combines with radiative cooling from the cloud tops to reduce the atmospheric stability. Thus, these storms develop rapidly. The storms can reach their maximum strength within 12 to 24 hours of formation, but they dissipate just as quickly, lasting on average only 1 or 2 days.
The fundamental question we're asking is what systems shape the weather? Again, we'll be focusing on air masses, fronts, the cyclones and anticyclones. The question of life cycle is important because that shapes how we think about how weather evolves and how we forecast weather again. And then the connections between surface weather systems and systems aloft. We've already talked about this, but we'll see how this plays out in terms of cyclones. And then how do systems operating at smaller scales impact weather? When we talk about air masses, fronts, and cyclones, we're talking from hundreds to thousands of kilometers. But there are also very important smaller scale processes at work that influence our weather, and we'll look at some of those at the end of the unit. Air masses are large regional bodies of air that adopt a certain set of characteristics. If you think about a stable mass of air in the upper left sitting over land, it generally will become dry compared to an air mass sitting over water. So if you have a weather condition where there's not much wind, you have a flat surface, you have the air sitting stably, so typically under a high pressure system, so clear skies, so that the ground and the air can cool or warm under the sun or cool through emission. The air is sinking, it's not rising and creating weather like in a low pressure system. High pressure systems generally give rise to air masses. If they're over water, they become humid. And so the map on the left shows the principal air masses that form over North America and generally how they move. As air masses move, they interact with the ground below them. A cold air mass moving over warm ground is warmed from below. As you know, you then get an unstable situation with rising air and mixing, and the air mass is destabilized. And air masses traveling from Canada down into the United States in the spring and summer are destabilized in this way, and you get weather associated with that vertical mixing. In the winter, air masses traveling down out of the Arctic or the polar regions over the lower frontier are traveling over maybe cold snow-covered ground, and in fact they're reinforced by the cold ground before them, and they remain stable and can travel a long way, and occasionally you get cold air outbreaks where cold air masses come down into Florida and destroy the fruit crops in Florida. There's an example in November 2011 of an Arctic air mass actually crossing over Alaska and becoming colder as it went, even though it was heading south, so that you got very cold air in the interior of Alaska that November. Fronts are the regions where air masses collide, and there's a lot of details about fronts in the textbook. I want to highlight here what's basically happening at a front. At a front, we've defined our air masses in terms of their density. Warm and humid air is lighter than cold and dry air, and therefore warm air can overrun cold air, or cold air will underrun warm air. In either case, you're getting vertical motion. The warm, less dense air is pushed upward. If it's more humid, remember warm air holds more moisture than cold air, you're going to get cloud development and significant weather. So when air masses collide at fronts, we get significant weather. I'm highlighting in this slide in the upper right warm fronts, a warm front moving from right to left, overrunning cold air. In the lower left, a cold front where cold air is moving from left to right, underrunning warm air. And then finally an occluded front where a cold front overruns a warm front, pushing the warm air upward, and the weather and cloud structure that you get in each case. I'm just going to highlight some very important differences. There's lots of details in the textbook. In a cold front, we're talking about cold air which is cold and dense and therefore remains coherent as it moves, and you get a abrupt bull-nosed front to the air mass as it moves forward, and it pushes the warm air up quite abruptly. And so for the cold front in the lower left, we see cumulonimbus clouds and cirrus clouds forming at the upper level. Winds are stronger at the highest levels, and the cirrus clouds blow out ahead of the front. Cirrus clouds are a forecaster for fronts coming. And the weather tends to be in a narrow zone at a cold front. In a warm front, we have warm air. It is not as coherent, not as dense. It can get stretched out as it moves, and therefore you have a much more gradual overrunning of the warm air of the cold air below, and you get a much more extended pattern of weather in terms of clouds, going from the stratus clouds all the way to the cirrus clouds. Curiously, it's at a warm front that you're more likely to get snow, because as the warm air overruns the cold air, it's moist, and it runs over a longer distance of the cold air, and so precipitation falls through a deeper amount of cold air below, and so it's more likely for snow to form. The other thing is that there's characteristic wind changes and pressure changes at these different fronts that can be used as forecasting tools. At a front, there are abrupt changes in pressure, temperature, humidity, and precipitation. The textbook doesn't do a great job of this, but it's important to recognize that in the idea of how a cyclone, a low pressure system forms, and the reason we're focusing on low pressure systems is because those are the ones with rising air and severe weather. So those are the ones we associate with storms. That there's behind the discussion in the textbook the idea that a cyclone has a sort of a six-step process, so that if you're following a storm, you sort of have an idea where it came from and where it goes. Not every cyclone follows this perfectly, but it gives you a conceptual framework. A cyclone starts at a stationary front where warm air mass and cold air mass come together and don't move much. The winds are at right angles to the front in opposite directions, and that creates a wave, that kind of fluid behavior, and we begin to get a wobble, if you will, or what's called a wave in the stationary front, and formation of low pressure on the cold side of the front. That then evolves into spiraling air around below and separation into a warm front and a cold front. In this case, spiraling counterclockwise. Remember, warm air is going to come up from the south, cold air is going to come down from the north. So if we spiral counterclockwise around below, we begin to create an entrainment of warm air coming up from the Gulf of Mexico, if you will, cold air coming down from Canada, and we begin to get a distinct cold front and warm front, spiraling counterclockwise. The cold front moves faster than the warm front, eventually overrunning it, and so that's when we begin to get occlusion. The occlusion grows, and eventually the cold front wipes out the warm front. We get to step 6. So there's a 6-step process that's in the mind of forecasters as they think about how a cyclone evolves. In the mature cyclone, we see very distinct weather patterns around the low pressure system. These are discussed in the book in terms of wind, temperature, clouds and precipitation, and pressure tendencies. I just want to compare that with the reality from the TV weather maps from NOAA here in Alaska, and you can see that it's much less textbook-like. We do see the pattern of an occluded front down in the lower right for tonight's forecast on February 15th. But we don't see the nice clear diagrams in the textbook. They're very conceptual. They're important. They're the underlying concepts. But in reality, on any given day, the weather can be a lot messier, even though these individual principles are at work. We've talked about Coriolis Force, and in the discussion of weather, there's a discussion of a concept called vorticity, and I just want to talk about it explicitly so that we've covered it for later work you're going to talk about. We know from the Coriolis Force that a parcel sitting at the pole will spin counterclockwise in a cyclonic direction. If you want, there's a natural low pressure spin in the circulation of the Earth. That parcel, if I move it towards the equator, will now keep its spin, but there's no spin at the equator in the Coriolis Force, and therefore a parcel heading from the pole to the equator will spin faster and faster relative to the ground underneath it, just by being displaced from the maximum spin at the pole to no spin at the equator. If I now go to the lower right corner, what I've done is drawn a upper air chart. If you want, these are isobars, showing the geostrophic wind traveling through isobars that are meandering. If I think about the ridge on the left, I have a parcel of air that maybe has some cyclonic flow. Not much, because remember, as the wind travels eastward around the ridge, it's essentially traveling as if it was traveling around a high pressure system, which is anticyclonic. So it has a low amount of cyclonic behavior at 1. As it travels south to 2, it increases its cyclonicity relative to the ground. As it travels to 3, it even has more cyclonicity relative to the ground and spins even faster. And then as it goes from 3 to 4, it slows in its cyclonicity because it's traveling north again, and the ground has a high amount of spin relative to it. So the idea here is that the cyclonicity of air parcels as they meander along in the jet stream between isobars, their cyclonicity relative to the ground is changing as they change latitude. At 2, where the cyclonicity is increasing, we get convergent flow. We get air parcels moving together. It's beyond the scope of this class to talk about all the mechanics of that, but it's a linked feature that occurs between cyclonicity and convergence. And at 4, as the parcel moves away from 3 to 4, we get the cyclonicity is reducing and we get divergence. And so we have this idea that as a geostrophic wind meanders north and south aloft, it creates regions of convergence and divergence because of changes in vorticity, and therefore it has important influences for what's happening at the ground. This view is seen here where we show an upper air chart. These would be constant altitude contours on, say, a 500 millibar map. Wind is flowing from west to east, meandering slightly between the contours as the contours meander, the jet stream through the middle of it all, the highest winds. And again, we see ridges and troughs, a ridge where the contours head upward or northward, and a trough where they come southward. And we see a connection between convergence aloft and the high pressure system below it, and divergence aloft and the low pressure below it. The wind spiraling into the low, converging at the surface below the divergence aloft, the wind spiraling out from the high, divergence at the surface with convergence aloft. And in this particular case, the picture doesn't try to show you the vorticity directly. It shows you just convergence and divergence through changes in the wind piling up or wind being pulled apart as it speeds up or as it slows down. Also the idea is that the highs and lows are connected to each other because the air rising in the low diverges aloft, and if you want, the high pressure system is the return circuit for the air to come down through the high on the other side. So we get air traveling in a circuit from high to low at the surface and then low back to high through the air aloft. The cyclonic flow is highlighted in this particular image, again showing the high and low at the surface, the convergence and divergence aloft, and the spinning of the air as it moves upward and downward between the jet stream and the surface. The summary of a cyclone here is just to give you a simple cartoon model of what's going on. Take the time to look at what's happening, where the convergence is, where the divergence is, that the ridge is to the west of the surface high pressure system, the trough is to the west of the surface low pressure system, the general motion, that the jet stream in some ways acts as a puppeteer pulling the surface systems along with it, the weather on the ground associated with the cold front, the warm front, the rising and falling air. This is a cartoon that you will see again. So make sure that you understand the general principles here. We'll be asking you questions about it in quizzes and exams. And it's not a figure that appears in the textbook. In terms of smaller scale winds, I just want to highlight two smaller scale winds. For those of you living on the coast, there is of course sea breeze and land breeze on the left. During the day, the land warms more than the sea, and therefore we get rising air over the land. If you want, you get what's called a thermal low pressure system at the surface on the land with rising air and air rushing in from the sea to fill that low pressure system, and you get a circulation cell with the pressure distribution that you see. At night we get a subsidence high pressure system as the land cools. The dense air falls, we get descending air, high pressure pushing out from the land to the sea, and then a return circuit aloft. As you look aloft, you're getting the pressure distributions that we've talked about between a warm air column and a cold air column. So we have slightly different things happening at the surface and aloft about how the pressure gets set up in terms of air sinking at the surface and being dense at night and creating high pressure. And aloft in the cold air column, the distribution of pressure that supports the whole return circuit of air. In the daytime, the sides of hills, when we look at mountain and valley breeze, the sides of hills are warm. We get rising air along the surface of the hills as the sun shines on them. And so we get clouds forming in the rising air, and then the air sinks in the valley and you get a return circuit. And again, we get pressure distributions that support that. And then at nighttime we get what are called drainage flows, and these can be very important in terms of cold air pooling in valleys and giving us very cold weather. And this can reinforce cold weather in mountainous regions or in valley regions, that you get cold dense air pooling in valleys and maintaining a colder weather than you would expect just from the synoptic conditions alone. The clear skies that might be under a high pressure system allowing radiative cooling at night. The last regional system I want to talk about is a Chinook. A Chinook can be driven by a cyclone or anticyclone creating winds across mountains. And on the right hand side we have a section of a mountain of moist air at 10 degrees Celsius being forced over a mountain. As it rises, condensation occurs, we get cloud formation, we get latent heat release. And so when we get to the top of the mountain, we have a wall cloud, seen in the bottom image, a wall cloud visible in the Rockies. And then the air descends. But now as it descends, all the moisture has been removed from it. And so as it descends, it warms, and all that warmth goes into the air itself. It doesn't go into re-evaporating the air. So the air actually warms to a higher temperature than it started. This can be explained by looking at the profiles on the left, where we lay out the trajectories of the temperature in the air parcel, the dew point temperature in the air parcel as it travels. Our parcel starts at point A at 10 degrees Celsius and rises in the first kilometer as a dry air parcel, changing 10 degrees Celsius per kilometer, so it cools to 0 degrees Celsius in the first kilometer. The dew point of this parcel was all of 2 degrees Celsius, and dew point changes with height 2 degrees per kilometer. And so the dew point cools to 0 degrees Celsius at B, and at that point the dew point and the parcel air temperature are the same. We have 100% relative humidity, and now we've got condensation as the parcel rises, and so now the parcel travels from B to C with its temperature changing 6 degrees Celsius per kilometer. It gets to the top of the mountain at C. It's now at minus 12 degrees Celsius, and it begins to fall down the mountain the other side, going from C to D. Because it's warming now at 10 degrees Celsius per kilometer, it's a dry process. All the moisture has fallen out through precipitation. The dew point from C goes to E, 2 degrees per kilometer, and so we go from a parcel at A, temperature at A, with dew point at F, to now a parcel at D, a higher temperature, with a dew point at E, a much lower dew point. And so by removing the moisture, the Chinook wind is much warmer when it comes down the other side of the mountain, and so it melts the snow, and that's why Chinook winds are often called snow-eating winds. We see these routinely in Fairbanks in the winter, where a cyclone or anticyclone in the Gulf of Alaska will set up a strong wind coming up over the Alaska Range. It also highlights that on the windward side of mountains we get a lot of moisture. We see this around the state of Alaska in a whole variety of places in southeast and south central. We get lots of moisture, good tree growth. On the leeward side of the mountain, a lot less moisture and a lot less tree growth. So closing thoughts and summary. Air masses bring distinct weather to different regions. The Arctic air mass brings cold, clear weather. The air masses of the Gulf bring warm, humid weather. A front is a boundary between two distinct air masses. Air masses are defined by their densities, and so when they come together at a front, they don't just mix into each other, they have a distinct boundary front with distinct weather. Warm and cold fronts have different weather patterns. Cyclones form at fronts and have a distinct life cycle that can be used to understand the weather and also predict the weather. Upper air behavior is a critical component of surface weather, and understanding of air masses, fronts, cyclones, and anticyclones provides a framework or model for understanding weather. Air masses and fronts are an example of what we call synoptic scale systems. Weather happens at smaller scales due to geography, and so local weather systems can be very important at smaller scales. It's not just the large scale of the weather systems that defines everything you experience in the weather.